So in this video, I want to talk about question 2. It's very similar to what we had done in question 1, so I'm not going to type it all back in. So here, what we want to do is we want to compute the z statistic every time. So here, we kind of, by default, the z statistic is being computed with a true mu, so the mu that's used in order to generate the sample. So here we again generate this. So we compute a mean sample, but instead of just returning the mean of the sample, we do mean of the sample minus mu divided by s divided by the square root of 89. So now we get 1,000 of those, and the histogram looks like this. So it looks kind of like a normal distribution. It's only ever slightly wider. Most of the observations for the t-statistic, so for this thing, are going to be between -2 and 2. That is the point of computing the t-statistic. So now we want the probability that the t-statistic is smaller than 1. So we can kind of eyeball it and say, well, I'll just cheat and look. So it's like 16%, looks about right. And we just do it by saying, well, how many of the t-statistics are below -1, what fraction of them? And the answer is 16%. So we can also do it using PT. So the way we do it using PT is we say Q equals -1. The degrees of freedom here is 88. Why 88? Because it's 89 minus 1. So we have two kinds of t-statistics that we know to compute. One is for one sample, so this thing. And the other one is we, with the x2 bar minus x1 bar divided by square root of s1 squared divided by n1 plus s2 squared divided by n2. And that would be distributed with the number of degrees of freedom. That's like the complicated formula, which we denote with the letter mu. Okay, so there's your problem 2. So problem 3 is like this. So we're using the same simulation, but now we're computing the t-statistic with a different mu, with mu equals to 8.5. So the situation here is that our null hypothesis is mu equal to 8.5, and that null hypothesis is false because we're still generating the t-statistic using the mean 9.47. Okay. So the point that we're trying to demonstrate here is that the t-statistic is not anymore going to be t-distributed. So a t-distribution has a mean of 0. And here you see that the mean is not 0. So kind of the mode, so the p here is, so the mode is just the most common thing. So that's 8.8. So now we compute the t-statistic because that's what the question asks. And the I was kind of, when I was writing the solutions, I was confused about what actually asked in the problem in the first place. So this is a correction. So here it's going to be 8.8 minus 947. And this, well, we can compute this value. It's going to be very, very far away from 0. -6. So the probability of observing that, assuming that it actually comes from the t-distribution with 88 degrees of freedom, is just basically 0. So here we compute the probability using PT. We could also say, well, like how often do we observe this t-statistic if we generated samples from the t-distribution? And the answer would be not very often at all. So now we're doing the two sample t-tests. So we generate data from 76 and 78. And we're just saying that mean is 9.8, DSD is 1.0 for both of them. And we're computing this t-statistic. So this is how we do it, right? So we generate this t-statistic. So now we want to say, okay, so what's the question asking? So we want to test the hypothesis that the means in 1976 and 1978 are the same. So this is just straight from lecture, right? So you compute the nu, and you compute the nu using all the information that you have from the data, which is the means and the standard deviations of the sample. And then you're saying, well, what's the probability of observing something smaller than the negative version of this or greater than the positive version of this? So we just do it with 2 times the PT of minus the F. So that's like the negative version. So it's kind of like whatever the T is, it's like whatever is to the right here or to the left here. And here we got a very small number. So here we get just basically a 0. And that's just because we didn't have enough samples. So if we had more samples, we would get something that's like the same. But like here, this is saying 2 twice in 10,000. So if you just have 10,000 samples, apparently we didn't luck out and we didn't even get the 2 samples.